This is my VP task project for the CIVE1143 complex analysis run by Sri. My name is Thomas Healy, and I'm just going to quickly run through some of the key results from my project. Run over 3 parts over VP task 1, 2, and 3. And we're going to be conducting complex analysis on this swing set you can see in the background. So this swing set is found in my local area. I go for walks around this area quite often, and I'm walking past this swing set all the time. And this swing set here is found in the Berwick Springs playground. It's a beautiful place. And what caught my eye about this swing was the fact that we have a mixture of wood and steel. And what makes this interesting is how the moments will be distributed across this, being that there's 2 different materials, this being a steel hollow section and this being a solid section. Now, in order to conduct analysis on this with consultation with Sri, what I've done is I have simplified this model into this. As you can see, there is a loading of 23.31 kilonewtons per meter on the top and the right side on the spans, B, C, and C, D, so on the steel. And to get this value, it was simply the last digit of my student number, which was 7, times 3.33, which gives you 23.31. Now, currently this structure has a DOI of 2. 4 reactions, 3 equations, sorry, this is 1. DOI of 1, 4 reactions, and 3 equations. So we're going to be conducting complex analysis on this model here, and we're going to be using 4 different methods: the force method, the slope deflection method, the moment distribution method, and the approximation method. And each of these methods, we will be aiming to come up with a shear force and bending moment diagram in order to compare. So the first method we're going to be looking at is the force method. And obviously the first step in the force method is to change our original structure to a determinant structure. So it's now determinant. So what I did was I changed this, which was a pin that had 2 reactions, and I changed it to a roller which has 1, and now it has a DOI of 0. And by looking at this structure, we can also take out the redundant structure and applying a 1 kilonewton load to the structure, to the joint in which I removed. And obviously it has a reaction of 1 kilonewton here. So we have this primary structure and redundant structure, and we can now apply formulas for displacement, FAA, and also use this equation to find the remaining reactions. Obviously, in this case, we're going to be taking EI as a constant, being that we're going to assume we're not going to take into account different I values at this stage. So the first step in the force method is to conduct some equilibrium analysis by taking moments at 3 different points relative to a displacement from each joint, x1, x2, and x3. And we can form equations through this using equilibrium, and we came up with these, which will give us the moment at any point along that member. And knowing that m1 will be equal to 0 since there is no horizontal forces acting on this beam. The same thing is done in the redundant structure. We're using equilibrium about these moments, and we're taking these as the real moments, and these are the imaginary moments. And what we do is we do the same thing and get our 3 equations for the moments. We can then apply these values into these equations. So obviously these go into this value, these go into this value. EI we keep as constant for now, and we also use this one in here. Then we can use this formula here, where we can take our displacement value, our FAA value, and solve for the remaining horizontal reactions. So we can find our reactions using equilibrium equations. The sum of Fy is equal to 0, the sum of X is equal to 0, and we can draw SFDs and BMDs. And here they are, my beautiful shear force diagrams and bending moment diagrams. As you can see, we've got our pin joints here, and the reactions are the same on both. And obviously, since they're a pin, there is no moment acting on the support. All the moments are essentially dissolved to 0. Next is the slope deflection method. Now for this method, I had to slightly adjust my model. As you can see now, we are now using fixed joints, and we are only taking a load on the vertical BC member. And this is at the discretion of Sri and the instructions that he gave, and he said to only look at the vertical UDL. For this one, it's a bit of a simpler method, a bit more straightforward. We're using this equation here, where we are looking at the moments at each point in the direction on the span, and we can use this to form our equations for the moments to attain any moment at a given point on that span. We're also taking the load of the moment at A to B. All these are equal to 0 because there are no horizontal forces acting on these members. However, on the top, we have an FEM for BC because we have a negative moment on the right side and a positive moment, on the left side, and a positive moment on the right side. Using this equation here, which is found in some tables, generic tables for different models, and these are the models that I use, WL squared on 12, which 12 would be, yes, given. Now, here are equations that are derived for the moments, each with a constant EI value. And we also have these unknowns theta B and theta C. So with our equations for all of our moments, we can, using this equilibrium condition, being that the moment here plus the moment here is equal to 0, and also the moment here plus the moment here is equal to 0 due to equilibrium principles. And we can form these simultaneous equations, which we can then use to solve for theta. And we find that theta B is equal to negative theta C. And from that, we can substitute these values into here, cancel out any EI values at this stage, and we come up with our moments at each point. Now, it's also worth noting that we can use these moments, we can solve for reactions, using how the shear force relates using these moments, and how the shear forces act on the reactions. And we can form our shear force diagram using our equilibrium equations, and also using the moments that we found previously, we get our bending moment diagram. And as you can see, there is also a moment reaction on a bending moment diagram because we are now using a fixed support for this method. And you can see our horizontal and vertical reactions on the shear force diagram. So the next method is the moment distribution method. And what this method does take into account is the different materials that each member is made of. So obviously AB is made of wood, as previously mentioned, and B, C, and CD are made of steel hollow sections. And what this method takes into account is the different E values and the different I values. So the E values that I'm assuming for this is 210 GPa for the steel, 40 GPa for the wood. Now the wood I've taken as a solid wood section. From the measurements I took on the playground, it was 130 by 130, and we can use this formula here to determine the moment of inertia for this member. And for B, C, and CD, we are looking at a steel hollow section with these dimensions here, and we can use this formula here to find the I values. And what's worth noting here is that the steel has a much higher E value and a lower I value, whereas the wood has a higher I value but a lower E value, which makes it interesting, which means that the EI values together are quite similar in magnitude. So the first step is finding these K values. And these K values will allow us to relate how the different members are distributed using distribution factors. So using these K values that we have obtained, we can then input into these distribution factor formulas, coming up with these values. And this is how the deflections will act across, and how they will distribute the moment across the frame. And what's worth noting here, which I have not written, is that the dF at AB is equal to the dF at DC, which is 0. We're taking it as 0 because we are looking at a fixed condition. And much like the slope deflection method, we're looking at a fixed condition. So all of the moments that go to AB and all of the moments that go to DC are absorbed. That's why I took it as 0. We also have an FEM acting on the frame, taken by these values. And the FEM at every single other point will be 0, due to there being no horizontal forces. So we come to this table. And what we can see here is that we have an FEM, and then the moment gets then released to the different members. Starting with this one, it gets times by -1, and this one times by -1. After that, these moments get released and distributed to the different joints. So this 18.85 gets multiplied by this value, and also this value to this point. So 18.85 times 0.323 comes to 6.086. And this value times 0.677 to get this value. And the same on this side as well. And next we have, obviously this becomes the distribution. And then we have carryover values as well. And through these carryover values, it is simply timesing each value by a 0.5, getting distributed like this. And like this, and each of these values getting multiplied by 0.5, and these carryover values are acting on the member. And after that, we have some more bending moments acting on these BC and CB joints, and these get released as well, times by -1, and we repeat the process, and then we eventually add up these values to get a number, and adding up all these values as well. All of these values, and we get the different moments acting at different sections of the frame, which we can then use to form our bending moment diagrams. And obviously, the same method as before, to find our shear force diagrams, we're just taking the reactions and making formulas for the shear force and how it changes over the different spans in regard to a certain displacement, X3, etc. So we can get our shear force diagrams. And bending moment diagrams come pretty much straight off the table. We get our values straight off the table. And we also have some reactions as well. So the next method, the approximation method, one that's a little bit more in detail. So we have our original structure from the start, from slide number 1. And what we're doing to it is we are, instead of making it a primary structure, we are taking these 0.1L values, which I've assumed, and assuming a hinge at this point, which then we can break down for this case 1. So we're breaking it down into 2 cases. Case 1 with a vertical UDL, case 2 with a horizontal UDL. And what we're going to do is we're going to combine those 2 cases. So for case 1 for the vertical UDL, as I said before, we're going to use these 0.1Ls to assume hinges here, where there is no bending moment. And as you can see here, I have just taken this section here, and we're looking for the reactions on these hinges using simple equilibrium. So the sum of Fy is equal to 0.
And then we are looking at this section here and this section here, which is shown in these diagrams here. And we are solving for the bending moments at C and B, again using equilibrium equations and using these R values as well that we've attained and putting them here. And next we are looking at the vertical members, applying the moment to the top and solving for this unknown reaction here. And obviously the AY and the DY is simply the shear forces on the top. So we have all of our bending moments now for case 1 and all of our shear forces for case 1. And we can then create our shear force and bending moment diagrams. Then for case 2, we have our horizontal UDL, and we're doing something a little bit different, explained by Shri in his tutorials. And we are splitting the section here right in half. So this whole length is 3.115. So this is half of that. This is half of that. And what we are doing is using equilibrium of moments at A and D, and using simultaneous equations for these two, because we're going to have two equations in terms of EX and EY. We can use simultaneous equations to solve for those reactions. And we can substitute those values in, and then we can do simple delta fx, the sum of all the fx values equal to 0, and we can get our AX and DX reactions. Same with the Fy, getting our vertical reactions. And we can then use these reactions to form shear force and bending moment equations, which allows us to draw the bending moments and diagrams and the shear force diagrams. As you can see, they're a slightly different shape between case 1 and case 2. I'll just show you the next one. So what we're going to do next is we're going to combine them. So here is a table. Each column has the shear forces from each diagram at particular points. And what I'm going to do is I'm going to add them together to get our new shear force. So what we're getting, so for example at this point where Vx is equal to 2, we are combining the shear force in case 1 and case 2, which had shear forces at that point of 36.305 and 20.66. And we get our new values here. So it's simply a case of adding them all together and also adding these reactions together. So this is our combined SFD for the approximation method. And the same applies for the BMD. We're just adding the two cases together to form these new values, and then just throwing these new values onto the bending moment diagram. So what we can now do is compare some of these values and compare some of these diagrams. So obviously we can compare the slope deflection method and the moment distribution method, because for both of those methods we used fixed joints. And we can compare some of these values. And you can see that they are quite similar. But obviously the main difference would be between the two values is that this is a much more symmetrical model because it doesn't take into account any E or I values. They are not accounted for, whereas this one does. And obviously because the moment is distributed unevenly, we can see that there is a non-symmetric distribution for this frame. But they are still quite similar in values. And it's just like the same thing with the bending moment diagrams. We can see that there is more bending moment on the wood than there is on the steel. More bending moment on the wood than there is on the steel. And also, from the slope deflection, we can see that, again, it's a very symmetrical model, but the values still fall within the same range. Very similar. And also the reaction here is going to be different because there is more moment on that wooden member. So we also can compare the force method and the approximation methods because they also use the same model. And we can see there is still some differences here as well, but you can see that roughly it's, very close, maybe 1 or 2 kilonewtons here and there in each place. And we can compare these values. They're very similar, and in terms of accuracy, I would probably lean towards the force method diagram in this one. Only because that 0.1 L that I took here was an assumption, and there might not actually be a hinge at that 0.1. So I'm going to take this as the more accurate model, but it's still good to compare. And again, we can see some very similar values, but perhaps off by about 4 to 5 kilonewton meters for each. And these should say kilonewton meters, not kilonewtons, which I'll have to fix. So just going back, go back. So yes, we can compare these bending moments and we can see that they're quite similar, but obviously there are some limitations to the approximation method, as it is an approximate method, but still, and then the force method is obviously a bit more in depth and gives us a bit more of an accurate answer. So my final thoughts, don't you love this slide, the 3D animation? My final thoughts on this project. Well, I think this has been a really challenging project. It's been a really good learning tool for me personally, being able to learn how to apply the force method, approximation method, and the slope deflection and moment distribution method, and apply them practically to a beam frame that I've seen in the real world. And I can see how the moment gets distributed. I can see how the moments act on the beams. And I think it was a great idea as a good learning tool that I've been able to use to help comprehend a lot of these concepts. And I think considering the circumstances, the team Complex Analysis has done a fantastic job, especially with all the lockdowns, providing this online learning. There's been a great, Shreya's been great through all the tutorials and has been able to help me really develop a lot of my structural engineering skills. So thank you all for watching, and hope you enjoyed.